Okay, so we're continuing on with normal probability distributions. In 6.1, really importantly, we looked at standard normal distributions. In standard normal distributions, the mean is always 0 and the standard deviation is always 1. Now in 6.2, we're going to cover real applications of normal distributions. In other words, we're going to continue on from 6.1, but we're going to look at real applications of normal distributions, where the mean isn't always 0 and the standard deviation isn't always 1. Okay, so key concepts in 6.2. This section specifically presents methods for working with a normal distribution that is not a standard normal distribution. For normal distributions, the mean is not always 0, the standard deviation is not always 1. Or some combination of these as well. So sometimes the mean is not 0 and the standard deviation is not 1. Recall that importantly, standard normal distributions have a mean of 0 and a standard deviation value of 1. In 6.2, we aren't going to work with standard normal distributions. Instead, we're going to work with normal distributions that more so reflect real-world applications. In those real-world applications, we're not usually going to see a mean of 0 and a standard deviation value of 1. So as we touched on previously in Chapter 3, there is a way to use a simple conversion that allows us to standardize any normal distribution. When a normal distribution becomes standardized, we make the mean 0 and we make the standard deviation 1. When we have a standard normal distribution, then everything we talked about in 6.1 applies. Now I mentioned there is a simple conversion factor, so here it is. If we know an x value, we know a mean value, we know a standard deviation value, we can convert these into a z-score. So as mentioned, this formula allows us to standardize any normal distribution so that the x values can be transformed into z-scores. Let's review these symbols. So the z-score is the number of standard deviations that a given value of x is above or below the mean. Remember from Chapter 3, a z-score can be calculated for both a sample and a population. X here is our variable usually used to represent the individual data values. We say usually here because sometimes variables can be represented by another letter, but we're mostly using X in this course. Mu is the mean of all values in a whole population. Sigma, or standard deviation, is the population standard deviation. Now, I want to point out something here. So we're going to make an x value into a z-score so that we can use the table or we can use Excel to find some given probability related to this x value. We need to do this when the mean is not 0 and the standard deviation is not 1. I want to point this out here. So what happens if this mean is 0 and the standard deviation is 1? Well, in those cases, we would have a z-score equal to x minus 0, so that's x itself, divided by 1. So in those cases where the mean is 0 and the standard deviation value is 1, z is equal to x. So in other words, z is equal to x only for standard normal distributions. When we don't have a standard normal distribution and we have some other value for the mean and some other value for sigma or the standard deviation, then we can use this formula to convert our x, mean, and standard deviation value into a z-score. Let's picture this now. So for example, in figure A, we have a non-standard normal distribution where our mean is not 0 and our standard deviation is not 1. So in order to take this picture A and convert it into picture B, that means we're going to make the mean be equal to 0. When the mean is equal to 0 and the standard deviation value is equal to 1, we think in terms of z-scores as we did for 6.1. However, when the mean is not 0 and the standard deviation is not 1, then we're not yet working with a z-score. We're working with an x value. In order to think along the lines of a z-score, we have to have a standard normal distribution where the mean is 0 and the standard deviation value is 1. Okay, now as just mentioned, these figures illustrate the conversion from a non-standard normal distribution into a standard normal distribution. For non-standard normal distributions, we have a non-zero mean and or a non-value of 1 for the standard deviation. I'll change this in your slides. This should be a non-zero mean and or a non-1 standard deviation. It can be either a non-zero mean or a non-1 standard deviation or both. That makes this considered a non-standard normal distribution. And then again, here for figure B, we have a standard normal distribution because we have a mean value of 0 and a standard deviation value of 1. One additional point here. So the area in any normal distribution, the area is bounded by some score of x. For example, where x can be here in this normal distribution. Using this formula for converting an x, a mean, and a standard deviation into a z-score, that's going to end up being the same as this area bounded by the corresponding z-score in a standard normal distribution where we do have a mean of 0 and we do have a standard deviation value of 1. So in 6.1, we went through standard normal distributions. Here we're going to go through the procedure for finding areas with a non-standard normal distribution. For chapter 6 so far, it's been important to think about drawing out what question we have and to think through it that way. So step 1 in this procedure is to sketch a normal curve, label the mean, and any specific x values, then shade the region representing the desired probability. Is it below that value of x or is it above that value of x? We need to consider these things because Excel and table A2 still tell us that cumulative area to the left. We'll do examples of this and we'll talk more about that. After we draw this sketch, we can either use Excel or table A2. So one version of step 2 here, using Excel, is to use the normal distribution function that we talked about in 6.1. Using the normal distribution function, we can find the area of the shaded region or find that probability, where for these cases, area is the same thing as probability because that area under the full curve is equal to 1. As long as we're thinking along the lines of cumulative area from the left, then this area is the desired probability that we're asked for in the question. Now we can also use table A2. But first, if we're using A2, we have a value of x. We don't yet have a z-score that we can look up along that first column and that first row. So we need to convert our x value into a z-score. To do so, we're going to take our x value, our mean, and our standard deviation, and then we get a z-score from there. Using Excel, we didn't have to do that. We could just use our x value as is, our mean value as is, and our standard deviation value as is. I will show you an example of that using Excel. If, however, you want to use table A2, that's only in relevance to z-scores. So to use table A2, you need to convert your x value into a z-score. Still keeping in mind whatever area you're finding is the cumulative area from the left, then we can use table A2, use our corresponding z-score, and find that given area or probability. Let's do this example now using both Excel and table A2. So we're going to answer, what proportion of men are taller than 6 feet? The information in the question that we're given is heights of men are normally distributed, so that's an important detail, with a mean of 68.6 inches and a standard deviation of 2.8 inches. We're asked to find the percentage or proportion of men who are taller than 6 feet or 72 inches. It is really crucial that we keep consistent with units. So if we're given a mean and a standard deviation value in inches, we should stick with inches here rather than using feet or some other unit like centimeters or something like that. You want to be consistent with all of your values. So for our solution, regardless of using Excel or using table A2, we want to draw out this curve and shade in the proper region. So reading through this question, if men have heights that are normally distributed, we can draw a curve like this. It's symmetric and it's bell-shaped. Once we have the outline of the curve drawn, we can denote our mean value here. So mu is 68.6 inches. Technically, the shape of the curve does change based on the standard deviation value. However, because we're only dealing with one standard deviation value, we're not really going to need to draw a standard deviation value of 2 versus 3. If we were comparing standard deviation values, then we could draw one curve to represent one standard deviation and another curve to represent a different value for a standard deviation. Here, however, we're only dealing with one standard deviation value, which is 2.8, so we can sort of keep that in mind, but we don't need to draw that within the curve itself. Remember from 6.1 that the larger the variance or the larger the standard deviation, the wider the spread is here of your normal distribution curve. The smaller the variance or the smaller the standard deviation, the thinner that curve is, the thinner the distribution is. So we've drawn our outline of our curve, we've drawn in our mean, we've mentally noted what the standard deviation value is, so 2.8. In the question, we're asked specifically to find the percentage of men who are taller than 6 feet. What side of the curve do we need to shade in then? Well, we have our mean value. We want to know taller than 6 feet or 72 inches in height. So then we shade in the region to the right. We want to know the percentage of men who are taller than 72 inches. So we shade in this region specifically. So as far as X values, we want to know the percentage of men who are taller than 72 inches, which is our value of X. You may notice down here on the Z scale where we have a mean value of 0 and then our converted Z value. At this point in the question, from what we've done, we would not know this information yet. When converting a non-zero mean value, or mu, and an X value, we need the standard deviation, the mean, and the X value to get our Z-score. In terms of Z-scores, we're going to eventually ask the probability that the Z-score is greater than our given X value, but we need this X value to be in terms of a Z-score in order to do so. To use Z-scores to have this X value be in terms of a Z-score, we need to adjust this X value so we have a mean of 0 and a standard deviation value of 1. Again, as is so far in the problem, we don't know our corresponding Z-score. We just know this non-zero mean, we know the standard deviation, and we know our given X value. We also know what area of the curve to shade under. Let's use both Excel and table A2. So first with Excel, we're going to use Excel's normal distribution function. This was discussed in detail in 6.1. Remember that both Excel and table A2 will tell us our area to the left, or cumulative area to the left. So using Excel, either this pop-up version of a function or typing the numbers into a cell in Excel, we need to think about our X value, which here is 72. Our mean value is 68.6. It's not a mean value of 0 here. Our standard deviation value, that's 2.8. That's given in the problem. Then we need to decide on this cumulative value. Remember, for cumulative values, if we want some range of area or probability, then we're going to use a cumulative value of 1. If we want to know the probability of exactly at one individual X value, that's a cumulative value of 0. Anytime we're shading in the graph in some way, that's a cumulative value of 1. Now, using Excel, we could use the X value as is. We didn't have to convert that into a Z-score. Why? Because this has an option for our mean value and an option for our standard deviation value. That's not 0 and that's not 1. We can plug in the true values there. But importantly, when we plug all this into Excel, it's going to give us our cumulative area or probability from the left. Because we want the percentage of men that are taller than 6 feet, then we shaded in the region to the right. So we can take this value we got from Excel and easily get our correct answer by using the complement. So we have our cumulative area from the left. To get the cumulative area to the right, we're going to take 1 minus 0.8877. That result is 0.1123. That's our correct answer. Now we'll get a slightly different answer using Excel versus table A2, but let's talk through both ways of doing this. As a reminder for Excel, we could plug in our X value, our mean value, our standard deviation value, and our cumulative value. We did not have to convert the X value into a Z-score first. But remember for table A2, all of those values are in terms of the Z-score, not some X value with some random value for the mean and some random value for the standard deviation. So in order to use table A2 here, we first need to convert this X value of 72 inches into a Z-score. To convert an X value into a Z-score, we can use this formula. We need to know the X value itself, the mean value, and the standard deviation value. Now, one thing again to keep in mind is that each of these values need to be the same unit, which they all are here. They're all in terms of inches. 72 inches, the mean is in inches, the standard deviation is also in inches. When we find this corresponding Z-score for this given X value, for this given mean and standard deviation, we get a Z-score of 1.21. Now that we have a true Z-score and not an X value, we can use table A2, look at the first left-hand column, look at the top row for our hundredths place, and find the area in that table, which we get 0.8869. Again, for our table, again for Excel, this reported area, this reported probability is our cumulative area from the left. So we need to go through the same reasoning we did using Excel. So as we did previously, we're going to take 1 minus 0.8869. We get an answer here of a probability value of 0.1131. So using Excel, we didn't have to do this. Using the table, we do first have to convert our X value, our mean, and standard deviation into a Z-score. For both Excel and table A2, we know this gives us our cumulative area from the left. So because we shaded in the right region of that curve initially, we need to take the complement, or 1 minus whatever area or probability we got from Excel or the table, to get our final answer here, to get our correct answer. So for the interpretation here, our area slash probability was 0.1131, or some number close to this, depending on if you use Excel or table A2. To interpret what this probability value means, let's convert it into a percentage and then think about what that percentage value really means. So we found the proportion or probability of men taller than 6 feet is 0.1123. Converting that into a percentage, that's 11.23. We took this, we multiplied by 100. In other words, we found the proportion of men taller than 6 feet, not equal to 6 feet, but any height taller than 6 feet. So using the less than, greater than, or equal to notation, we found the proportion of men with a height greater than 6 feet. Now, as we talked about in 6.1, you might be required to find a given value from a known area or probability. So let's talk through the steps for doing so. So again, these are the cases in which we're given an area in the form of a probability or a percentage, and we're asked to figure out either the known Z value or the X value. This suggestion comes up again, so graphs are extremely helpful in visualizing, understanding, and successfully working through problems like these. Helpful hint number 2, again, don't confuse the Z-scores and areas. This was also mentioned in 6.1, where the Z-scores are the distances along the horizontal or x-axis scale, but the areas are regions under the normal curve. In table A2, the Z-scores are in that left column, and then across the top row for the hundredths place, areas are found in the body of the table. Helpful hint number 3, choose the correct, either the right-hand side or the left-hand side of the graph. For example, a value separating the top 10% from the others will be located on the right-hand side of the graph. So the top 10% might be a Z-score and X value about here. Whereas the value separating the bottom 10% will be located on the left-hand side of the graph. So the bottom 10% would be an X value here, and then the numbers to the left of that, the area to the left of that. Okay, this step is really important because either using Excel or Table A2, we're always finding areas to the left. So if we're asked about the bottom 10% or the bottom whatever percentage, that's also any probability less than that given percentage or given value. For a probability for the top 10% or the probability greater than some X or some Z value, that's shading the area to the right of the curve. If we're dealing with the top 10% or top whatever percent, or dealing with finding a probability greater than some known value, that's when we need to use the complement and take 1 minus the cumulative area from the left. So this helpful hint number 3 is really important. Number 4, a z-score must be negative whenever it's located in the left half of a normal distribution. This was mentioned also in 6.1. Importantly, with either negative or positive z-scores, we're going to be looking at a different part of the table in Table A2. It's also important to recognize either the negative or the positive z-score because it tells us where to draw the line on in a curve like this. So negative z-scores will be to the left of this maximum point on the curve, and z-scores that are positive will be on the right-hand side. Helpful hint number 5 is that the area, which is the same thing as the probability in this case, they're always between 0 and 1. We know that, we've reviewed that a few times, and they're never negative. We can't have a negative probability score. So probability or area values are always 0 to 1. They can be 0, they can also be 1. They can't be negative, and then as far as percentages, they'll be either 0 to 100%. Okay, those are some helpful hints. Now we're going to go into the steps for finding values from a known area or probability. Number 1, surprise, we're going to draw a graph first. So sketch the normal distribution curve, enter the given probability or percentage value in the appropriate region of the graph, where the probability or the percentage value is the area. Then once we have the graph drawn out and the given area, we want to identify the X values that are being sought after. We can do this with either Excel or Table A2. So for Excel, we're going to use that normal.inv function, or the normal inverse function. This was talked about in 6.1. Let's review it again. So we want to find a given X value or a given Z-score given a probability value. To use the normal inverse function in Excel, we need that probability or the area value, for example, 0.975. We also need the mean value. It does not have to be 0. For a standard normal distribution, it is 0. We also need the standard deviation value. It also does not have to be 1. For standard normal distributions, the standard deviation value is 1. So we can use this normal inverse function for either standard normal distributions or non-standard normal distributions. The only 3 numbers we need for either case are the probability/area value, the mean, it doesn't have to be 0, and the standard deviation value, and it doesn't have to be 1. To set up that function in Excel, we would start typing equal sign to set up any function, then norm.inv. The first number in that formula is our probability value or area value. Importantly, this probability or area value needs to be from 0 to 1. You can't use a probability value that's in a percentage, so you need to convert that out of a percentage first. Then comma, the mean value, comma, the standard deviation value. Click enter, then you'll get your X value or your Z-score. Importantly, Excel takes that probability and assumes it's the probability or the cumulative area from the left. Then it gives you that corresponding X value or Z-score under that assumption of cumulative area from the left. Now we can also do step 2 with Table A2. We know in the body of Table A2, those are corresponding area or probability values. If we have a given area or probability value, we want to find that. When we find that on the table, we'll have our corresponding Z-score. Now, if you use the table and you know your corresponding Z-score, but you're actually asked for the actual value of X, then we need to convert that Z-score. To go from a z-score to an x value, we can do that as well, just using a different version of the formula we saw earlier. If we rearrange this formula of z is equal to x minus the mean all over standard deviation, we rearrange this to solve for x, then we can find x given a mean value, a z-score, and a standard deviation. Remember, when we're dealing with z-scores, we're assuming a mean value of 0 and a standard deviation value of 1. When we want to know the equivalent x value, that means that we have a mean that's not 0 and or a standard deviation value that's not 1. So we followed step 1. Step 2 can be either using Excel or table A2. Then step 3 is to check, does the number that we found make sense given the problem and given our original sketch of the situation? It's really important to check here. If you ended up shading in some region to the right, but you're reporting the cumulative area from the left, then check that and make sure the value makes sense. Let's do this example now where we know the probability or area value, but we want to find the given z-score or our x value equivalent. For our example here, when designing equipment, one common criterion is to use a design that accommodates 95% of the population. Here's more context. We have seen that 46% of women satisfy the height requirements for US Air Force pilots. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of heights of women. To solve this, we're going to assume that the heights of women are normally distributed with a mean of 63.7 inches and a standard deviation of 2.9 inches. In addition to the maximum allowable height, should there be also a minimum required height and why? So in the question, we're asked to find the 95th percentile of heights of women. Let's do a quick review on percentiles. For example, if we have this graph with age on the x-axis in months and then the weight in kilograms on the y-axis. Then if we're interested in the 90th percentile or 98th or any other percentile here, then let's look at the 98th, for example. Then we look at all of the ages and weights under this orange curve and between this blue curve. So a child that's a certain number of months old, that weighs a certain amount of kilograms, if it falls between this orange range and this blue range, it's considered to be in the 98th percentile. Additionally, if we were looking at a child that's in the 90th percentile, they would fall below this blue line, but above this red line that separates the 90th percentile from the 75th percentile. For even more of a review, we initially looked at percentiles in 3.3. There we defined percentiles. So percentiles are a measure of location which divides data into 100 groups with about 1% of the values in each group. For example, we can have the 99th percentile, the 98th, the 90th, etc. Let's review how we solve for percentiles again, given a specific data value. So if we want to find the percentile of a given value, a given weight, for example, a given height, for example, we're going to take all of the number of values less than that specified height or weight, for example. Divide that by the total number of values that there are, multiplied by 100. So in other words, we're recognizing that the 99th percentile, we would calculate that percentile as being the 99th percentile because 99% of data values are less than that given value that marks the 99th percentile. Let's apply that reasoning now back to our example where we're asked about the 95th percentile for heights of women. In our solution, we're going to draw a normal distribution curve. We know our mean value is 63.7. In the question, we're asked about the 95th percentile. Based on what we just reviewed, we know we could draw some line somewhere. We don't know the x value or the height yet that corresponds with the 95th percentile. What we do know is that the 95th percentile corresponds to an area or probability of 0.95. So 95th percentile, divide that percentage by 100, we get 0.95. So here we drew a normal distribution curve. We shaded in this area to represent 95%. or 0.95 of the total area under the curve. We know our mean value, but we don't know the height that corresponds with the 95th percentile. Step 2 now, let's use Excel first. So we can use this normal inverse function, either using the pop-up version of the function or typing in numbers directly into cells in Excel. So for the normal inverse function, we need a probability value or an area, we need our mean, and we need our standard deviation. I included the units here because we want to remember to be consistent with our units. Keeping in mind when I type these things into Excel, the reported value here is going to be taking into account that 0.95 is the cumulative area from the left. And it is in this case because we're looking at the 95th percentile of heights of women. Based on the definition of percentile, so going back here to this equation, we're finding the number of heights less than a given height. We don't know that value yet. What we do know is that computing all of this gives us a percentile value of 95%. What we're basically asking here is what is the top 5% of heights of women? In other words, what's the cutoff between 95% of all heights of women from the other top 5% of all heights of women? So when we compute this with Excel, we get an X value or a height value of 68.47 inches. To round this off, let's say 68.5 inches in height. Incredibly importantly, I'll mention again, remember the probability or area value, so this 0.95, must refer to the cumulative area from the left. For the 95th percentile, we're really interested in the area or probability from 0 all the way up to that percentile or 0.95. Let's try this now with table A2. So we know our percentile, it's 0.95. We know this percentile refers to the cumulative area from the left. So we go to our table, we find 0.95 in the body of the table, then we find the corresponding z-score. Remember, for any probability or areas above 0.5, we're looking at a positive value for a z-score. For any area or probability values less than 0.5, then we'll be looking at a negative value for a z-score. If you don't have that memorized or you weren't thinking about where you were looking and you try to look for 0.95 in the negative z-scores, you wouldn't see it there. So then you go to the positive z-scores, find the area or the probability value of 0.95. Now, when we're not thinking in terms of z-scores, we have our mean value, or 63.7. We know the shaded region under the curve is 95%, or 0.95, of this whole area under the curve. We don't know what height or X value yet. That splits the 95% of women who are the shortest from the 5% of women that are the tallest. When we want to use table A2, we have to think in terms of z-scores. So we still go to the table, we find 0.95 in the area of the probability, so in the body of the table, we find a corresponding positive z-score of 1.645. Now, this is a special case where we're using table A2, and this area has a star by it, has an asterisk by it. This is because when we go to table A2, we're not going to see 0.9500 specifically. Instead, we're going to see the areas of 0.9495 and 0.9505. If we go to the footnote, we'll see that an area in between these two values, so 0.95, the probability value we're interested in this question corresponds to a z-score of 1.645. Now there's an additional step because we have a z-score, right? We really want to know an X value. We want to know the true height, not the z-score. So from table A2, we found our z-score. From the question itself, we know our mean value. We also know our standard deviation value. Then we can use that formula that includes z, mu, and sigma to find our given X value. One version of that formula is z is equal to x minus mu over the standard deviation. We plug in what we know for z, mu, and sigma. We get an X value. We can also use this version of the formula where we've rearranged to solve for X directly. So X is equal to mu plus Z times sigma. Our mu, or our mean value, is 63.7. Our z-score, what we found from table A2, is 1.645. Our sigma, our standard deviation from the question, is 2.9. This leads to an x value, or a height, of 68.4705 inches. We're keeping consistent with the units. Everything here in the question was in terms of inches. So the answer we get for our x value is also in inches. Now, that's definitely the correct answer, but we always want to check and make sure we're thinking along the right lines here. So our solution was x, or a height of 68.5 inches. This reasonably makes sense because our mean value for the height of women is 63.7 inches. Because we're interested in the 95th percentile, the height value that we got, the x value that we got, needs to be greater than our mean. Recall it for our mean, or 63.7, it's going to fall right here in the middle of the normal distribution. This mean then is where 50% of this curve is shaded to the left and 50% of the curve is shaded to the right. So it makes sense with the percentile of 0.95, where 95% of the curve is shaded. That's going to be equivalent to a value that's greater than the mean. Now, there was one more part to our question here. So in addition to the maximum allowable height, should there also be a minimum required height, and why? So let's continue the interpretation here. A requirement of a height of less than 68.5 inches would allow for 95% of the women to be eligible to be US Air Force pilots. Now, that sounds great that 95% of women would be eligible. However, it might make more sense to consider the minimum requirement for more practical reasons, such as so the pilot can easily reach all the standard controls. That is the end of 6.2 now, so hopefully it's clear when we're working with standard normal distributions and non-standard normal distributions. I will see you next time for 6.3. As always, let me know if you want to check any of your work from the U-Tries or talk through any concepts at all. See you next time.